In this video, I'll show you how to use accumulation functions to construct antiderivatives. First, let's remind ourselves of what an antiderivative is. If you have a function f, then big F is an antiderivative of little f if the derivative of big F is equal to little f. For example, if little f of x is x cubed, then big F of x would be 1/4 x to the fourth plus some constant c, because the derivative of 1/4 x to the fourth plus c is x cubed. But what if you had a function like e to the negative x squared? You can't use the power rule or rules for exponential functions. Unfortunately, none of our basic derivative rules work. The formal way to say this is that f of x doesn't have an elementary antiderivative. It turns out that you can actually use accumulation functions to construct antiderivatives. Let's look at an example and think about it in terms of velocity and distance. We'll start with a graph. Here are a set of axes. We'll think of the function v of t equals e to the negative t squared as describing the velocity of a car. We can draw a graph of this velocity function. Next, let's think about an accumulation function. Here, d of x tells us the amount of distance the car accumulates between time -3 and time x. We want to know about the rate of change of this accumulation function. For example, if we imagine the distance accumulating, we can ask, how quickly is the distance accumulating when x equals -1? It is difficult to determine this because the rate seems to be constantly changing. To make things a little easier to think about, let's imagine a Riemann sum approximation of this total accumulated distance. Let's think about what this Riemann sum is telling us. If we look at one of these bars, we know that it has a width that corresponds to the amount of change in time. In this case, 1 second. Also, it has a height that corresponds to the velocity of the car. Now, the reason this bar has a horizontal top is because we're assuming that the velocity is constant through the entire 1 second interval. And when we multiply the constant velocity by the amount of change in time, we get the amount of change in distance, which is represented by the area of the bar. Let's think about the rate of change of distance with respect to time, just for the interval between -1 and 0 seconds. Since we're assuming the velocity is constant, then the rate of change of distance is the ratio of the amount of change in distance and the amount of change in time. When we do this, we're dividing the area of the bar by its width, which gives us its height, which is representing the velocity of the car. Let's take a closer look at what this means. If we start at -1 seconds and imagine the value of x increasing, how quickly are we accumulating area? For this bar, its height tells us how quickly we're accumulating area as x increases. So the value of v of t tells us the rate of change of distance as we increase x. Similarly, if we keep increasing the value of x, now we're accumulating area at a much faster rate. Once again, the value of v of t tells us the rate of change of distance as we increase x. And we can imagine doing this using a Riemann sum that had much shorter intervals. In particular, for each value of x, the rate at which we would accumulate area would be given by the height of the graph. That is, the rate of change of distance would be given by the value of the velocity function. And if we shrink our time intervals enough, then the rate of change of distance with respect to time would be the same as the instantaneous velocity. Thus, the derivative of our integral, d' of x, is equal to the velocity function evaluated at x. Let's think about what a graph of the accumulation function would look like. For each value of x, the value of the accumulation function, graphed in black, tells us the amount of distance we've accumulated between time 0 and time x. We can see that the value of the velocity function tells us the slope of the accumulation function. And now, since the derivative of the accumulation function is equal to e to the negative x squared, this means that d of x, the accumulation function, is an antiderivative of e to the negative x squared. So, in general, if you have an accumulation function, a of x, for a function f of x, then a of x is an antiderivative of f of x. Another way to express this is that the derivative of a with respect to x is equal to f of x. And this is one part of the fundamental theorem of calculus.